sediments. You can do like a rough kind of back of the envelope calculation and show that for thickness of typical of 10,000 kilometers, you get an additional vertical stress on the lithosphere that is about 220 megapascal, and that is well inside the range of other geodynamic forces. And an interesting thing too is, well, we can clearly see that there is a generic link between geomorphic, tectonic, and sedimentological evolution of the continent and the offshore regions. So you kind of need to look at these things together if you want to understand the system. Okay, so going through the kind of interaction we can expect, the first thing that comes to mind is, of course, isostasy. So we know that loading or unloading a plate, when removing or adding material on the plate, will translate into an isostatic response. So here I took the example of Montgomery, 1994, and an example of in the Wind River Range in the USA, showing that preferential erosion of valleys results in a slow decrease of the mean elevation, but an uplift of peaks. And what they did in this study is they basically calculated the rock uplift caused by erosional unloading, and came up with estimates of a few tens of meters, typically 50 to 60 meters, for a different elastic thickness. So, and over a range that is, in this case, because we're talking about glacial erosion on an area that is much larger than where the glaciers were actually. So it's quite small in amplitude, but it's enough to create a slope, and that will eventually add erosion, translate into an erosion. And in you see actually the same kind of thing in raised system along passive margins, where depending on the kind of model you consider in terms of the evolution of the passive margin, you so whether it's a classical rift margin model or down rock model, you predict total erosion of several. I mean, if you just consider isostasy, you predict a total erosion of of several kilometers, which I mean has been shown also in terms of fission track ages profile. So something quite important. Another effect that we can expect as I mean rock are exhumed is I mean heat is also exhumed. Heat is also advected to the surface, and this translates in this does affect the rheology of the lithosphere, making it weaker as I mean, temperature is affected, as heat is affected. And so you can look at simple things like the Becquerel number that measure the ratio between diffusion and advection, and do some quick calculation on how this affects the lithology, the rheological profile. And this can, so the temperature, of course, is going to weaken well, the lithosphere, but there is also a component of I mean, with deformation, you have like interaction between these two things. The lithosphere becoming weaker locally, we tend to localize the deformation. And this kind of processes has been proposed to explain the evolution of the Himalayan syntaxis, and was called like tectonic aneurysm in the Namaga Parbat, for example, by Zettler in 2001. So conclusion is the isotome deflection can result in rapid deformation locally. Of course, erosion is going to be a function of the topographic gradient, and depending on the erosional pattern, you may also influence the gravitational potential energy field. And here is again an example that has been proposed to explain some of the feature of the Himalaya by Romain et al., where I proposed that part of the lower part of the Tibetan plateau may actually flow and be sensitive to erosion at the surface. And we predict that we should actually see the same kind of phenomenon in rift system, where we can expect some kind of an effect of both crustal thinning that will result in flow of weak lower crust inside the basin, but could actually be countered by sediment loading into the basin, which actually may revert the flow toward the rift shoulders. And this kind of processes has actually been proposed to explain some of the feature of passive margins around Australia that we, as a research group, are interested in. Talking about the Northwest Shelf, where simple conceptual model proposed that initially weak lithosphere, which tend to distribute deformation within the lower crust, could actually change its rheological behavior through time because of loading with sediment and flow inside the lower crust, which eventually will result in a stronger lithosphere and more localized deformation. And of course, erosion and sedimentation can alter the stress field. Here I'm showing two examples from the literature of coupled models, so 2D and 3D, one from Romain et al. 2000, one from Thermo et al. 2014, where when the main effect of erosion on this model is localization of the deformation along some major faults. And an important paper also to mention is a paper from Olivier et al. 2014, which we looked at using a simple model of viscoelastic plate over a viscous mantle, showed the effect of sedimentation on faulting, and coming with a conclusion that low erosion tends to result in multiple short-lived faults with a small offset, while when erosion approaches the extension rate, well, you get more major long-lived faults and large offset. Okay, and of course, just to quickly finish this part, climate and erosion are, well, it depends on topography, so, and we should expect feedback using climate and erosion. And that's actually what has been proposed to explain, part of the metamorphic, the gradient, the kind of metamorphic rock we observed on the cropping in New Zealand and Olympic months, depending on where the precipitation comes from relative to the main tectonic structure. So just to quickly resume the kind of feedback we see. So the transfer of gneisses due to surface processes, so including erosion, transport, and sedimentation, have the strong potential to influence continental dynamics whether it's through isostatic rebound and flexure of the lithosphere, perturbation of the geotherm, changing gravitational potential energy, or changing the stress field. And as erosion and climate are both influenced by topography, we expect dynamic feedbacks between crustal, lithospheric deformation, and surface processes. So we have quite a complex system where so tectonics mainly result in crustal thickening, isostatic uplift and deformation, which translate into enhanced relief, enhanced basin size in some case, enhanced erodibility. And while erosion, which is through fluvial incision, mass wasting, or glacier infiltration, reduce gravitational stress, erosion height, and area. So interesting coupling to investigate. We know from numerical model and others that what actually control deformation of lithosphere is its rheology. It's gonna version true in rift settings where you tend to have a wide rift when you deal with weak lithosphere and narrow rift when the lithosphere is strong. And all of these, of course, varies depending on the rheology, so the composition, crustal thickness, heat flow, strain rate, etc. And it's going to translate into different topographic expression that will influence your erosion pattern. So we have several technical challenges that we need to address if we want to build coupled thermo-mechanical models coupled with surface processes. Some are quite general in terms of numerical modeling. So it's like, so what kind of spatial and temporal resolution do we need? How do we scale the models? How do we calibrate them, of course, and how we provide uncertainties. So it's challenging because we are dealing with different physics. And question is, what kind of rheology should we use? What kind of, should it be viscous, viscoplastic, or what about elasticity? Do we need to include elasticity? Boundary conditions are always, they are very important, of course, but well, the way we model isostasy in this case, I think can be problematic. And and of course, how do we reconcile the timescales, and whether we need 2D or 3D, and how we deal between short and long range transport with models that are usually quite limited in extent. So the way we do that here in Melbourne, so we use our in-house code called Underworld. So we develop both 2D and 3D models. The models I develop because I'm mainly interested in looking at a rift system or a classic layer model with viscoplastic rheology, which are temperature, pressure, and strain rate dependent. I also use temperature and pressure dependent densities. So, and in terms of boundary conditions, so we use at the base different ways to model what I call like pseudo isostasy. So it's actually something that we prescribe in the model, and an extension force of at the boundaries. It's a rift model. And so we use both 2D and 3D models. The 2D models because they are easy to run and they take less time. And 3D models are a bit more challenging, of course. So just to quickly mention that the code is, our code is available online there on GitHub if you want to have a look. There's also a series of examples that we provide. And in terms of surface processes, I use a different code, but the main one is Badlands, which is a code that is been developed by Tristan Sall in Sydney. So Badlands solved for the classic power law equation using a series of forcing conditions, so one of them being the uplift, so the position of sea level and the precipitation pattern, and of course erodibility of rock. So Badlands solves for fluvial erosion essentially, is subdiffusion, and has a pretty efficient offshore sedimentation algorithm. Right. So the coupling is achieved using a module called UWGeo that is also part of the underworld code tools. So the way we do that, we get underworld to solve for the thermo-mechanical model. So we solve for pressure, velocity, and temperature using the Stokes equation. And that advection, and we transfer the surface advection to Badlands. Badlands deal with erosion, sedimentation, updates the surface morphology, and in return, that module calling UWGeo update the material in underworld, and we run that through time stepping. And again, this is available online on GitHub. So I'm quickly going to show you some models that I've been working on. The idea is to look at evolution of a rift with different phase of rifting and cooling. Today, I'm just going to present you the first phase of rifting. Yeah. Whoops. And then I'm going to quickly show two cases where I either use a strong rheology, scaling the wet quartz follow by a factor of 30, and weak crust rheology with a normal wet quartz follow of 1. And this is, of course, coupled with surface processes. So this is one of the model I've done. So this model, this specific model is actually what we call a T model. So it's running a 2D underworld model under a Badlands surface. This model, so that kind of constrains you to a symmetrical model. But these models are very useful because they can be quickly run in like a few hours. Very useful to calibrate for calibrating the free ones. So I'm just going to show you a quick video so you can see how the coupling performs. So you see that as the lithosphere is extended, of course, you start to see fault appearing, and so you get topography forming at the surface that is eroded. That model is quite it's quite aggressive in terms of I mean, the crust is quite strong and the erosion rate is quite high. So you get like a lot of sediment coming to the vessel, and the sediment loads fault and tend to localize deformation along this road. All right. And of course, we can do where we can predict the amount of erosion and total sedimentation. So the same model, just looking at the surface at the erosion in blue and deposition in red, and so underneath you have the material of the thermo-mechanical model, underworld model. Actually, that model is different because it's more symmetric. All right. So quickly, gonna go through some results. I run with another code actually, and some paper that have been submitted recently to PSL and showing basically the same model I presented before. And so what you have in this panel is so a model with a strong crust, so and coupled with surface processes. So here it's coupled to a basket code by Jean. And so on the left you've got the low erosion case, and on the right you have the high erosion case. What you see first is well, you don't really change the geometry of your rift just because you add sedimentation, but there are some interesting features appearing at the surface. In the case of the low erosion, the water divide at the surface is quite well defined, and you end up having sharp topography, sharp transition between the onshore and offshore. While in the high erosion case, well, the water divide becomes much harder to follow, like very quickly. And so you get you load the fault with sediment, which translate into some emerging basement height that you can observe in passing here, and increased offset along the fault. In this, that also tends to delay deformation and development of new fault inside the basin. So looking at the total erosion and sedimentation at the top, so erosion in blue and sedimentation in red, and that the second invariant of the stress for the thermo-mechanical model, what you see is that you actually have much localized high stresses in the case of sediment, where you actually load the sediment, while you get lower stresses under area that have been eroded. And an interesting feature too is this basement height tend also to be eroded. So you actually have quite an amount of reworking of material. And here, what I'm showing is a second example where actually I'm using a much weaker rheology for the lithosphere. So the thermo-mechanical model has a weaker rheology. And what we see is so here again, you're not really changing the overall geometry of the rift, but you still have some. You still see some feedback. Of course, because the crust, the lithosphere is weak, it can't really support high topography, so you don't have much topography to provide that gets eroded and provide sediment. But even in the case of the high erosion, it's not like you wipe out the topography entirely. You actually have some morphology that appears at the surface and evolves. So quite a dynamic response between the two. And in terms of stresses, well, the stresses are not really affected. I mean, it's barely noticeable. But you have large part of the surface processes model that shows reworking of sediment, mobilizing of sediment from the basin. Okay, so the next step is actually to go 3D. So as I mentioned, the model I showed you before are T models, so there are 2D thermo-mechanical model coupled with surface processes, so in a T manner. But of course, these systems are intrinsically 3D. You want to look at the transfer of sediment, the surface between faults and ramps, and so you kind of need to go 3D at some point. So I'm just showing here like some preliminary results we got with Claire Mallard from the University of Sydney, where we look at oblique rifting. So we've got a simple underworld model, similar to the one I presented before, but with boundary condition that results in an oblique rift, and balance coupled on top. And what we are starting to look at is actually at the stratigraphy, because that's something we can actually extract from our models. So we're still actually debugging those models, but I think they are really promising. Of course, the question is, how do we calibrate those models? So as I said, we can predict the amount of erosion and sedimentation. For a model like this, which I said, I think this one has quite strong rheology. The total erosion, so strong rheology means that it's going to translate into quite high topography and quite large amount of erosion, and so quite a large amount of sediment deposited in the basin. But we have estimates that in terms of erosion are the order of several kilometers. So quite extreme, but not off by an order of magnitude. I think we are in the right order of magnitude. And same thing for sediment, with prediction of typically 5 to 8 kilometers of sediment, which is, I think, agrees with what we observe. And of course, you can derive erosion rate and look also at the idea would be also to look at the temperature evolution of the rock as they are being exhumed toward the surface. Something that we think we could compare to prediction in terms of thermochronological ages or things like that. And as I said, so the model, thanks to Badlands and the work that has been done in Sydney, we can extract stacking patterns, Wheeler diagram, and boreholes from these models, which we are planning to use to compare to simple natural cases. All right, I'm a bit ahead of time, I think, but yeah, just a quick set of conclusions. So I think surface processes are very important, but tectonics remain the main control on structural evolution. We can expect multiple feedback in terms of isostasy, thermostructure, rheology, and etc. But these, we do require a control experiment to understand how these. These feedback are quite complex, and we think that a good place to do this is using numerical models. But of course, there's the classic dilemma of simplicity versus exhaustivity. These models are overly simplified, or simplistic if you want. And we are in desperate need of a link with field studies, like finding interesting natural examples where the effect of surface processes is clearly established, and where we can actually extract over effects such as mechanism. All right. Just want to mention that our codes and the models which come as Jupyter notebooks are available on GitHub, and you can contact me or Louis if you want to have access to these. So I'm a bit ahead of time, but we can do questions or.
Yes, thank you, thank you very much, Romain and Louis. And now for everyone in the audience, if you would like to ask questions, you can either ask them through the chat window or unmute or click on mute and then ask them, and then ask them that way. Anyone? Well, if no one else does, I have a few questions.
Yeah, okay.
So the first one is from a technical perspective, there must be all sorts of complicated details when you're dealing with the coupling back and forth between these two codes. And so my first question is, for anyone who's looking to do this with their own code, what pitfalls should people be aware of? Are there any real technical difficulties you had to overcome? Subtle ones, perhaps.
In terms, so if anyone wanted to do that with their own code, I guess if it's from a technical point of view, it really depends on the code. So the way we, our API is quite simple because we have a good Python interface. So all the coupling is done through a Python module. But in terms of, so I guess you think in technical pitfall, yeah, well, the time stepping is important. So you kind of need to take into account both the criterion that constrain your time step in the thermo-mechanical model, but this can be also affected in the by how much erosion you have and how much deposition you have in your passing. So the way we do that is, for now, we use quite a small time step in the thermo-mechanical model. So it's typically a few thousand years. And that's a limitation. And that's sub-stepped. So you've got sub-stepping in bad lengths that adjusts its own time step in function of its own criterion. And some, I don't know what's.
I think the other thing that we struggled with over the years of doing this is some of the very simple things like how isostasy goes into the problem, where
yes, yeah.
you know, I mean, there is a complete separation between things that are above sea level and things that are below sea level in the way that the surface process model deals with things, and yet all of the sort of dynamic basement modeling code is really hard to calibrate to something as precise as sea level, right? It's a few meters will make a big difference, and you're actually looking at large, many tens to hundreds of kilometers of the mantle involved in how that process goes, right? So the whole dynamic topography plus, you know, isostasy in the sense of a global readjustment for small changes somewhere. That's a really, really hard problem that you know, to explain is incredibly simple, and to solve is just horrible.
Yeah, I don't think we have done that yet, but yeah. Very, very sensitive. A few meters make a huge difference. So.
In terms of the properties, I'll just ask one final question, and then it looks like there's a number of questions in the chat window. Do the properties you assign to sediments affect these kind of things? So in my mind, I always imagine, like, if you erode a material, the resulting sediment should have a lower density and perhaps thermal conductivity. And so in the context of thinking about isostasy, do things like that, that properties you assign eroded material affect things quite a bit?
Yeah, so for now, the model are simple in the sense that the sediment has roughly the same property than the crust that we erode, except for density, because density is the obvious one you want to change. But which also change the mass balance in a way. But yeah, I agree. I mean, you also changes the thermal property of your material. So you've got, you could deal with, yeah, so sediment with low diffusivity, or change the the temperature field in the basins, for example. So yeah, that's very important. For now, we are trying to keep it simple, but we expect to have like feedbacks at many levels.
Thank you. Are you able to see the questions in the chat window?
Yeah, we can see them.
Yeah, I think we are.
Okay, great. It looks like the first one is Merrick Kogel.
This is the first one's from Eric Cowgill.
So first one is do the model include or approximate the effect of melting or at a developing ridge? Well, we can add melts in terms of we can. It's not two-phase flow model, so we don't have we don't extract melts, but we can account for change in the thermal field because of melt and change in viscosities, things like that. But it's pretty simple. It's not extraction of melt. Second question from
maybe just jump to the third one, which is sort of related to that.
Does the thermo-mechanical model consider reworking of rock metamorphism and magma production? No. Basically, no. No. Something else?
But that's worth coming back to, though. I mean, there's an awful lot of the stratigraphic work would be on at least understanding compaction and then moving into some sort of metamorphism. So, yeah, what is the technical issue associated with that? I can think of some, but I'll let you answer some of that. You know, what is the sort of what stands in the way?
In the way of what?
Of dealing with sort of the compaction of sediments and how that would work, and the metamorphism as they get buried deeper.
Well, yes, for any change of phases, you have like change in volume and stuff like that. But you need to take into account that kind of goes against the idea of that affects our mass volume.
Yeah, so I think that if I were to summarize a bit of what I think there is those things, the difficulty with that question about the whether the thermo-mechanical model considers the reworking and metamorphism is that to some extent this is sort of really we worry about what goes on which side of the interface, right? So we treat this coupling as being a sharp interface where there is a sort of a geodynamics component, and then there's a very thin line, and then above that is sort of a surface process component. And at some point, that's really not true. And this is sort of that question addresses where it's really not true. That somewhere is that there is a real sort of blending of the surface processes right down into the geodynamic model, and we have not dealt with that in any way. And that's kind of interesting, just philosophically. It's very interesting because we just don't build a couple code that way. So. And I think we already see there's a bunch of issues associated with how with the path we've taken with having two separated codes, which is an easier path. It's already extremely complicated. So, yeah, yes and no.
Yeah. So
Ting's got two questions now.
Ting's got two questions. So when coupling bad and underworld, what special things do you need to consider? For example, the time and vertical resolution may be different. Yes. So yeah. So there's obviously some interpolation steps, but as any interpolation, well, you kind of lose information in the process. So usually what I do is I've got the model I showed up quite low resolution in the thermo-mechanical model, but we barely go below 500 meters. You can obviously do much higher resolution in the surface processes code, so a few hundred meters. So as I said, that means you need to interpolate velocity field you get from the thermo-mechanical model. And so, yeah, there are some, from a technical point of view and from a scientific point of view, you have to be aware of that and be careful what you're doing. What else? I think you mentioned climate, tectonic, and erosion. How will climate be added to the system? So well, I'm not gonna couple it to climate models, but I mean there are simple things you can do in Badlands. You can change the direction of wind. You can of course change the precipitation pattern. You can do orography, precipitation. So that's what I mean by climate.
And you've got another question from Romain. The coupling Badlands and Underworld, what is the effect of the dynamic grid in surface process models? And how often do you have to re-grid Badlands?
So the grid in Underworld is static. Okay. In Badlands, it's a tint, so it's a triangulated mesh, and it's well the remeshing is it's kind of adaptive. It changes through time, injecting new points where they are needed, and so it's not really a regrid step. Though I think the person to ask would be more interesting. Yeah. What do you think in terms of minor?
Well, there is a fundamental question there in terms again of what the two of how you deal with that interface, which is at two different resolutions, and so there are some parts of that are sort of sitting in the coupling part of that module, right? So there really is a sense that you need to have a sort of a horizontal and vertical strain rate that comes from the basement code, the underworld code in this sense, right? And that has a resolution that depends on its particle distribution. And that may be you certainly don't want to be taking that and then multiply interpolating between it and the very fine grid model of the surface process. So you want to sort of take the changes at sort of a slightly longer wavelength and transfer those across to the finer grid of the surface process model. And then I think the issue is whether or not there are real decisions that get made in that coupling process. You know, you to some extent this is left open to the user to do according to the problem that's in question, because I think sometimes it will be necessary to sort of regrid a lot, and sometimes it won't. So we often try to leave these things to be free for somebody to know what they're, to do it themselves, to figure out how to do it. And the dynamic grid, in a sense, is always going to be regridded to be optimized because it's one of the low-cost components of the problem compared to all of it ends up being pretty low cost in terms of computation compared to solving a 3D basement deformation problem. But it's not necessarily low cost in terms of storing all of that information at very fine time steps. So it's not clear to me that you come up with a generic answer to that problem, to that question actually. Okay, next question is, in what specific directions would geodynamic and surface models effectively link with field studies, and are there ongoing efforts now to address this need? We could almost pump that question and say that the CIG and the systems, the CSDMS group held a workshop earlier in the year, and I think one of the big things that came out of that workshop was that we didn't know the answer to that question, and as a community, as two communities, we need to come closer together to even begin to address it. And we may have our own opinions on that, but we did contribute to sort of that overall discussion, and it's a really big question. So, Romain, do you have an opinion on it?
Well, in my opinion, it's really needed. I mean, we can't. we really need to have input from geologists and people that know what's going on. But of course, our models, they are limited in what they can do, so we can use them to understand processes, but they are no way able to reproduce nature. So
yeah, I think there's an issue that the mantle and lithospheric scale problems have pretty small number of jumps between scales, right? I mean, the scales can be quite large, but if we understand the rheology of olivine, for example, we get quite a long way to understanding how to build a global dynamic model. And I know we can quibble with that, and we can say that maybe if you want to understand faults better, you have to open up this problem. But when you actually look at the sort of subgrid assumptions that are built into what are relatively simple equations of the surface process problem, it's not always clear to me that there's an obvious link between how those things get put together and what the continuum version of this problem looks like. So it's quite a hard problem to address from first principles, and it's very yeah, I don't know what to say. I don't want to tread on toes there with the whole community, but it's quite a hard problem to see how to make that connection. But thank you, John. That's great. That's a link to the white paper. There's a lot of people put effort into addressing this. All of it. Well, that question that we're sort of struggling with. It's we're not struggling with it because it's something we haven't thought of. Everybody has thought about this, and we know that it's a real problem.
Are there any additional questions? If not, I guess we'd like to say thank you to Romain and Louis again for putting together this excellent presentation and for doing this again on such short notice. And for everyone, again, there will be a second follow-up talk to this one on January 31st, which will be on a new parallel surface processes code written by Dr. Moresi. All right, thank you again, and we'll have a good holidays, everyone. And we'll be looking forward to seeing you in the new year.
Yeah.
Thank you again, Romain and Louis.
Thank you.
Thanks everyone for joining in. Thank you.